Okay, so let's get started. So we are discussing reinforcement learning, and today we'll have a presentation. Are you ready?
Yes.
And you mailed me the presentation?
Yes.
Okay. So, yeah. So this we will have maybe in the next lecture, and this one we are going to have today. So remember we talked about the agent and the environment framework, where environment has a state, agent has an action, and then depending upon the action in different states you get the reward, and the agent's objective is to maximize the discounted reward. And we formulated it mathematically, and we said that we defined this Q function that tells you the total reward, the discounted future reward and the present reward. And we gave an algorithm for learning this Q function, because once we know what the Q function is, then we can actually optimize, right? We can just take at every step, at every state we can take the optimal action that maximizes the Q function. And we gave the proof of convergence of the Q function, and this was for the deterministic case. And the other case that we discussed was the stochastic case, where the reward and the next state are all stochastic, and this leads to what is called a Markov decision process. And the simplest example of this is a multi-arm bandit problem, where we have, let's say, slot machines, right? And different slot machines have different rewards, but the rewards are stochastic in nature. So this would get Ri. So this, for example, could be R1, R2, Rk, and we want to find expected Ri, right? Max over I. This is what we are interested in, finding the slot machine that gives you the maximum expected reward. And for that, we have to apply what is called a explore-exploit strategy. So again, your QTA would be the reward for action A, right? And in the ith step, right? So in the ith step, if you take action A, then you get a reward, and since it's a stochastic reward, then we can actually approximate it with this, and total number of times action A is taken. So with this we can create some kind of a QA. Right now the action A is not dependent on the state, right? But we can create an expected reward. We can get an estimate of the expected reward by updating the QTA. And in the greedy method, at every step, what's the reward? What's the action we take? That which maximizes QTA. But the problem is that our estimate for QTA may not be correct, right? You might have taken a particular path, a particular slot machine, and it gave you low reward, but its expectation may be still very high. So to do that, to actually fix this problem, we do what is called epsilon greedy method. So with probability 1 minus epsilon, we are going to pick an action that maximizes, and with probability epsilon, we pick a random action. So this is the explore step, and this is the exploit step. Okay? This is clear. So now how do we generalize it to a general problem? So now we have a Markov decision process. So we have a set of possible states, again a set of possible actions, and now my reward is a distribution over state action pair. So for every state action pair I get a distribution, and there is a transition probability for state action pair and a discount factor. And this transition probability is also dependent on state and action. Okay. So what happens at time t equal to 0? You sample from some state, and then the agent knows about this state. It chooses an action t, and based on this the environment rewards one sample of this, and then environment samples the next state, agent receives the reward RT and state ST plus 1. and then you iterate over this. A policy is a function from state to action, which will tell you what action the agent will take. It could be stochastic. We can start with deterministic policies. We want to find an optimal policy that maximizes the cumulative discounted reward, but in the expected sense, right? So in the expectation, I want to minimize the reward. So what do we want to do? Expected sum of rewards, same as before, gamma to the power t, rt given pi, given an action, given a policy. The only thing that has changed is, now these are stochastic variables and I've created an expectation over it. Okay? And the next state is also a function, it's a stochastic function. So the expectation is taken over all possible next states and then all the actions of those policies in the next state and so on. Right? So it is somewhat non-trivial because you are at state st and then let's say you take an action at, then your next state could be one of these, right? With some probabilities, right? So P1, P2, P3 and so on. And from this state you can again go to next state with some probabilities, again depending on the policy pi. So this expectation, when it's taken, it's not only taken over the reward but also over all possible next states. Right? So how do we solve for this recurrence now? So again we can define the value function V pi s. You know, if you have a policy pi, what is the expected reward when you start with the state s? This is again expectation of gamma to the power t, reward at time step t, given the policy pi, and so that your starting state is s. Right? S0 is s. You start with the state, what's the expected reward you get? And similarly we can define the q value function. Q pi s comma a is the expected reward when you start with the state s and then take action a. Right? And rest of the time you apply the policy pi. Right? So at the first step you take the action a. In the first state, when you start with state S0, you take action a, and rest of the time you apply policy pi. So that is q star s comma a, and it's the expectation taken. And the same relationship is there between q star and the reward. This v function that we discussed before. Now, how do we learn this policy? How do we learn this q function? And the Bellman equation says that the q star, the optimal q value function that gives the maximum expected cumulative reward, is given by the expectation if you already knew this q star for other states, right, s primes, and all the actions, then you can get qs of a by just taking the expectation of this function, right? So this is the reward, the maximum reward in the next state s prime, and this is the expectation taken. What's the probability distribution that you go to the next state x prime given the action a, right? Over that probability distribution, and you look at the reward at that step. So that's the expectation. That's how you get the q star function. So essentially it's the same as before, except that you just replace the reward and the next state with expectations of the reward and expectations of the reward in the next state. And once you have the q star, your optimal policy can take the best action given the q star, because now q star already incorporates the expectations. Okay, so you can find the action that optimizes the q star. So you're not going to go through the proof of this, but that's the basic idea. So how do you actually update your q s comma a at time step I plus 1? Let's say I already know it at time step I. Then what do? I take the maximum action, the action that maximizes this qi s prime comma a prime, right? So that I can find the reward that, the action that maximizes this. But now my next state s prime is a random variable. So what I do, I take expectation over this random variable s prime, because if I state s, if I take action a, then the next state are random variable. So for each of the possible next states, I find the maximum action, the best action there. And then I also take expectation over the reward for that action. And I add that up. And that's how I update my Q to Qt plus 1. Fine. This is exactly what we discussed before, except that we are now, instead of deterministic, we are making it expectations. Okay. Now, what's the problem with this? Why will this not work? Or what is the issue? The issue is that we can have very large number of states. And, computing this QSA for every state action pair becomes cumbersome. Right? It requires a lot of time you visit those states. And, because, remember the proof that we did for the Q learning algorithm? At every time you come back to that state after visiting all the other state and action pairs, the error here decreases by factor gamma. Right? So you have to do it many, many times to do that. So what this means is, every state action pair you have to visit many, many, many times before you can actually converge. And this may take a long time. So what do? We approximate QS, A using a neural network. So far what we talked about is just general reinforcement learning without neural networks. But now what we are saying is, to learn this we use a neural network. So now my neural network has parameters theta, and this network actually takes state and the action as the input and tries to approximate Q star S, I. Right? And that's a regression problem. Right? Given S, A, I want to estimate what my reward is going to be. How can you learn this network? You can use different architectures. I can use multi-layer perceptron, a 3-layer neural network, or a deep network, all those things. But the question is, how do I learn that network? So for that I need to know Q star S, I. But we started with this that we cannot get Q star S, I because there are so many states, so many things. What we have is a Q star S, I estimate of Q star at time step t. So we use each of those estimates as the input to my neural network. And using that I try to optimize. So what do? We want a Q function that satisfies this Bellman equation. If I optimize this with a neural network, I already have this with the neural network. Because I've already started with some neural network, right, with some weights. I already have an estimate using these weights. Right? So what do? I come up with a new estimate, I take the action, look at the reward, and give that as the input to the neural network. That's one of the inputs. So what happens? So what's my loss function in my neural network? So this is at time step I. What's my loss function? Is yi minus, so yi is the actual expected reward, which is Q star S, A. And Q is what your network learns, the approximation of that. And I'm looking at L2 squared error. Okay. Now, yi in reality, actually we want it to be Q star S, I, but we don't have Q star S, I. So what do here? I replace it with the current neural estimate at time step I minus 1. So I use the current neural estimate by my neural network, and using this I find the maximum, the action at the next state. I take the expectation over all possible future states, and I look at the reward and I take the expectation over it, and that's my yi. That's my label for the current state. So as I go playing this game, I take an action, I get one sample for yi. And using these samples for yi, I learn Qs, A, theta I. Right? So you remember we look at, so it's sort of like, kind of like a regression problem, but my yi's are given in this particular way, which are again dependent on the weights at each step, right? Because this is dependent on, this term here is dependent on the neural network that has been already learned. So what's my algorithm? I can do epsilon explore and exploit. At every step, I can take the best action with some probability, let's say 1 minus epsilon, and other steps I can take with some random probability epsilon. Epsilon could be a small number. So I'm doing explore and exploit. Whenever I take the next step, I get some reward. I get a next state. I can use that to estimate my R and the distribution over the next states. And that's one example for my neural network. I use it to optimize my parameter theta. So every step I take, I update theta. Again take one step, I again update theta. And that's how the neural network works. But this is, we talked about forward propagation, right? What is yi? How do you do back propagation? Because how do you update theta? So you have a current value of theta, you get this qs prime a prime using that value of theta. Using this, you can compute the loss function. How do you back propagate? How do you compute the new value of theta? You have to take the gradient of the loss function with respect to theta. And the loss function is this, I can differentiate it. Yi is already known because it depends on theta I minus 1 previous iteration theta. But now I am updating with respect to the current theta. So this becomes a constant in that case. So I take the derivative and then I back propagate. So I can write the equations for a derivative. You basically have to take the derivative of this Q function that I am approximating with the neural network. And once I take this derivative, my rest of the machinery I had from the neural network side, can be applied, right? Step size selection, deep networks and all kinds of things, right? So we iteratively try to update the Q function as we learn and make it as close to the target values yi as possible. And over time, hopefully, we are going to converge to the optimal policy or optimal Q value function, which will in turn lead to an optimal policy pi star. Right? Because once I have the optimal Q function, then I can just take the action that maximizes the Q. Right? If I know Qs comma A. Okay. So the next is this paper on playing Atari games. Right? That's what you are presenting today. So I'll stop here.